Good afternoon, this is Schweitzer, and this is a series of videos on I call School of Acid Base, start to finish. Last time we talked about how do acids produce hydroxide ions, or H3O plus ions, or hydronium ions. And we mentioned that they go through a reaction. Every acid reacts with water to give it an H plus ion, a donator, and then this reacts to produce H3O plus ions, which we know is sometimes it's written as H plus because it was mislabeled for many, many years, and then X negative. This is called the hydrolysis equation for acids. So this little video is going to work along with what we call same idea, but how do bases produce hydroxide ions? And it turns out that bases maybe would be a tad bit more complicated, or they have an alternate path. Okay. Let's cover the hydrolysis first, because we just did that on the last one. It doesn't matter which one we do first. So there are some bases, and only weak, well, we don't know what weak means yet, but you hear the term weak acids and weak bases. Weak bases, in this case, undergo hydrolysis, and we're really not going to, even though we'll have lots of them, there really are a few that we'll talk about, and I would say even ammonia might be one of the rare few that we'll specifically talk about in this class. And ammonia will react with water. Now remember that an acid is a donator, and a base is going to accept. So in this case, we're going to have this guy be the acid and this guy be the base, and the water will donate. Now in the last video, the water accepted. Now the water is donating, so the water is either going to accept an H plus to go to H3O plus, or it's going to donate to form OH negative. Something that can do both acid and base, both accept and donate, or chemically react like an acid, or chemically react like a base, we call oHproduction. I'm thinking like amphibian. It does both land and water. Alright, so the result of this. Okay, this is a snapshot before. What's the post snapshot? Take away H plus from the water, give it to this guy. That's going to form NH4 plus, and we have OH negative. In this case, I'm going to connect up my conjugates. This should be quite simple. That guy and that guy. This is the base. This is my conjugate acid. This is my acid. This is my conjugate base. Okay. In this situation, that's pretty much it. That's the main character we'll almost always deal with. You could have something else, but you'd literally have to deal with it like an X negative, where we have, in this case, X negative. In my last video, I used HF as a weak acid, so F negative is considered a conjugate base. Alright, so each of these works the same form. I'll just do the F negative plus H2O yields. But water donates to the F negative, giving me HF and OH negative. And at this point, we have a situation where we have, this is the donator acid, this is the base, this is the conjugate base, and this is the conjugate acid. Now you might say, well, okay, hold on a second. How can this thing be basic if we're making an acid? That's something that always confused me when I was going through this. It turns out that HF really isn't acidic. HF is only acidic once it goes through hydrolysis. And that reaction is happening only ever so slightly because the concentrations of this guy are very, 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 very small. So, that being said, it's all one big tug of war or stalemate, and in this situation, the hydroxides outnumber any H pluses that would be present from that acid, and it will therefore be basic. Alright, let's try the alternate method. Now it turns out that acids, and you might watch a video on how to name acids, and we'll probably eventually throw this into this little series, name acids. acids have their own special name. I don't really know why. I'm guessing because they developed through society in our foods and a lot of things much earlier and to a much greater extent than bases. And therefore, people just acquired a way to give them names. Bases, on their hand, don't have any names. They are just simply ionic, which means we have a cation and an anion. Specifically, that anion is hydroxide. Okay? And the cation can vary. So, for example, NaOH is a very common ionic hydroxide. And at this point, you should be aware that when we dissolve NaOH, we just get two cations floating around separately, Na plus ions and hydroxide negative ions. And this is a very effective way to get lots of hydroxides into solution very quickly. So then the chemical formula is Na plus OH negative. And therefore, this is a really great way to produce bases. And this is often referred to as a strong base. We'll talk more about that later. But in some sense, this is purely based off of solubility. Now, hydroxides generally aren't soluble, at least not very soluble. There are a couple of them that are very soluble. Sodium hydroxide, in this case, potassium hydroxide, maybe lithium hydroxide. Someone might, argue for calcium hydroxide or magnesium hydroxide. Looks like this. And they're just starting to become less soluble at this point. But these are some common items that tend to be considered strong bases potentially. These two are fringe, but only because their solubility starts to drop off. And therefore, it will start to collect on the bottom as opposed to dissolve. And therefore, we just don't get as high concentrations. So an acid and a base can both produce their respective acid-base component using hydrolysis. And you might notice that the formulas aren't exactly the same, but they're close. The base template is going to be X negative plus H2O yields HX plus OH negative. I have the acid one right above it. The base version has an alternate method, which is just determined by solubility of an ionic compound. All right, so with that said, how do acids and bases produce H plus ions? There you go. And these hydrolysis equations we will be using lots as we move through. Thank you very much.